All right, boys, welcome back to Ox Tools. I'm Tom. So what we're doing today here is we're going to do a baby bullet question and answer, or answer anyway. So we did this, what I call this kellering here. And, I don't know if that is the actual official term for that, but kellering machines used to leave a kind of a pattern like that. So some people would call that a kellered finish. And the machines basically used a ball end mill and they were tracer mills. And, they took little steps like this. So that's where I think that term came from, that term for that finish. The method that we used is basically it's a series of coordinates to drive the end mill to. Okay, so we'll talk about that in a second. So I got a list of questions here. Some guys put in some really good questions. So let's kind of jump in and go into it here. Okay. One of the first questions, or a couple of people asked, "Gee, how are you gonna, align those jaws when you go to do the welding, right? Since we have, this kind of spherical area here, right, and this doesn't sit on it very well." Well, the plan is, this is the sequence, here's the plan, is once this is shaped nicely and I lop it off, it'll get attached to the fixed part first, okay? And aligned basically, this parallel with this keyway here, right? The little keyway. I didn't bring all the parts over here. So that'll be attached, and this is going to be our basis here. Well, the other part doesn't have this keyway in it yet, okay? And I think that's part of the key, haha. So we'll just stuff that in there, right? Like so, and it'll be free to rotate, right? What we'll do is we'll make a dummy jaw that indexes this pinhole here and the same pinhole over here. So it'll be a rectangular piece of material that we can close the jaw on and clamp it, and then this will be in position in its bore. Okay. So the whole key is to weld this jaw on first, then this jaw will be a slave to this one, basically. Okay. Like so. So there'll be a piece of material that has a dowel pin in it or something like that to register it, okay? So that they're registered side to side, and they're registered kind of in this attitude here, okay? Move over a little bit. Okay, all right, so that's kind of that, answering that question. Okay, now let's talk about this one, because this is the one with the little anvil on it here, okay? So a bunch of guys said, "Oh, hey, that could become the anvil." Well, you're absolutely right, it could, but not in this case, not in my build. It can be in your build, but not in my build, because I kind of already made the piece separate, and I made it separate because the material that I spec'd out, in the parts list was only big enough to make 2 jaws with just very little extra material. It's in the interest of saving money. Guys could just cut that right in half, or machine the jaws, kind of mirror images on either end, right, and still have something to hold on to. Now I ended up with a longer piece, so I ended up with a handle, okay? But I had already made this little monkey here, so this is the there it is. There's the little tail piece there. So that'll just get welded on. And I'll make one on camera just so you guys can get a look at that and how I do that. So that's part of the build. Also, I didn't cut the radius down far enough to become part of that. I would have had to plow that down even farther. I don't think there was a reach problem. I think my boring bar was long enough, so technically I could have done it, but I just didn't. So because I was thinking I had already planned it this way. So One thing that I've found is, you know, you do design work and you sit at the computer there, right? And you come up with a plan. Well, what you don't want to do when you're at the machine is be trying to change your plan on the fly. That's when you get into trouble, or I've gotten into trouble, is changing that plan. So, so don't change your plan at the machine, you know. Go back to, if you think you want to change it, go back to the computer, think it through, or go back to the layout and think it through before you start changing stuff, okay? Just a word to the wise. Mr. Bozo lives in that territory. Okay, so let's see, we showed that. All right, let me, so next we'll talk about the actual Kellering method, so, or what I use to determine the coordinates. Okay, so here's the layout with the coordinates, and actually let's do the upper one first here, okay? And I did this in AutoCAD, okay, and it's quite simple. This is the center of the radius right here, okay, that little circle, and that's the quadrant of that circle right there, okay? And then I drew a radius of what I went and looked at to see what tools I had, and I had a 1/2-inch ball end mill, you know, 12.7 millimeter ball end mill. I said, okay, I'm going to use that. And then what I did was I drew a circle here, or a half circle, and in AutoCAD there's a function called a polar array, okay? And what a polar array is it arrays it in a circular pattern about a particular center, right? So I said, okay, I want to array this radius 10 times, or whatever that is. What do we get there? 1, 2, 3, 4, 5, 6. Yeah, okay, roughly 10 times, okay? And then, actually, I'm just going to draw on this, okay, because I don't even care anymore, right? So there's an angle here, right? And in this case, it was 41 degrees, I think. So I said, I want to array 10 of these within 41 degrees, okay? So I just did it, and that's what it came out. And you could do 8, you could do 100, you could do as many as you wanted, okay? And in this case, I just did 10 because I have a large end mill and a small, you know, 5-degree steps is probably plenty to give you a nice smooth curve, okay? And you can look at the cusps between those radii, and see, and it's probably hard for you to see, but there's a teeny dash of white in between there, pretty small, okay? So by doing a lot of steps, you get a smoother finish, but, you know, I was planning on doing, you know, some handwork anyway, and these are pretty small, so I'm not going to worry about it, right? And anyway, for videoing, it's easier to do it quicker, okay? So anyway, that's how that was created. Now, you can also do this on graph paper, and I'll show you how to do that, okay? I'll show you that in a little bit. So this is basically the same thing, okay? This is the same thing, but our center is out here in this case because it's concave, so, all right? And for those of you that don't remember your high school geometry, this point and this point, okay, if you draw a line between those, like that, right there, that's the point of tangency between those two curves, okay? All right, so right there, okay? And then now, let's address one more comment too while we're here. Somebody said, oh, well, you got a DRO, that makes it really easy. Well, remember that these are all driven from one spot, okay? So we start here, and we're moving the mill this way, and we're moving the mill this way. That's it. We're not going back and forth. So we just keep adding, okay? We're just adding in one direction. So you can zero the dials when you're here, and you're just scooting over. Okay? It's not that hard, okay? And you can, you know, very easily do the math on this so that they can be incremental steps if you want, okay? You can arrange it any way you want, all right? So in this case, it's just a total So even without a DRO, this is totally possible. Okay, so let's move on to the next thing. Okay, so I get this question a fair amount actually, and let's grab the tool I was using there. So somebody asked, they said, hey, why do you use oily oil, or why do you use misty mist? So oily oil and misty mist, okay? So the difference between these two is this is, it's oil, okay? What's really nice about oil is it's very, very slippery, okay? So you tend to get really good finishes, and yes, it does do some cooling, okay? But it's better at producing good finishes, okay? And also it is the best for reducing friction. So tapping is a good example, or something where you're taking a very light cut and you want to reduce friction and have a slippery, nice surface, okay, for chips to flow off of and the cutter to go across, okay? So that's oily oil. Misty mist is much better at cooling, okay? With carbide, it's not as sensitive and to that, in the home shop, I should say, all right? It's high-speed tools, yes. These things get hot and you can overheat them pretty quickly. So they perform better when you cool them, okay? This is not as good at cooling as this is, okay? Now this has a little bit of oil in it, so it produces good finishes as well, but it's much more effective at cooling, okay? And this produces a lot of heat. It's got a lot of cutting edge. There's a lot of chips in there, and there's just generally a lot of heat, okay? Now, the downside of this is it makes a mess, okay? So those are the things that I'm balancing. I'm going, do I want to make a mess? Yes, I want to cool this off, and that's why I want just a tiny amount, okay? I don't want smoke. Okay, so those are some of the decision points on whether to use misty mist or oily oil, okay? So oily oil definitely for tapping and fine finishes, okay? And misty mist definitely for when you're willing to make a mess at the expense of getting good cooling, okay? Now, if you have a coolant recirculating thing or an enclosure or whatever, it's kind of a non-point. All right, so this next question, so somebody commented, I was going back and forth and kind of removing the material back and forth in this attitude, right? Well, one of the reasons was I already had it clamped this way, so it sort of made a little bit of sense. Now the other way that you can attack this that they pointed out is that you can plunge in Z, okay, to carve out that material, which is actually a pretty effective technique with the right end mill, okay? Now the end mill that I was using is happened to be a non-center cutting, so I'm limited to up to the width of that cutting edge, okay? And if I go to the center line, then I'm not gonna get there, okay? So with the right tool, you can do that. Now the other way to attack this guy here, you could also attack this in a very similar way, okay? All right. Now the downside to that is you can see that we have a very long reach, and end mills, when you get beyond about 3 diameters, everything starts getting squeaky and dicey, in particular in tougher materials or harder materials like steel. So this is, yes, another way that you could do that. You could go to those coordinates and just kind of poke that material out that way and do it that way if you don't have a ball end mill, okay? So that's just another, and it's, Z plunging is good. The machine is very stiff that way, but as you can see, the bandsaw is the fastest for cutting that material away, right? Following those curves nicely, I have a 1/2 inch wide, a 13 millimeter wide bandsaw blade, which doesn't turn real sharp. So, and I wanted to use this technique on here anyway. So, Okay guys, we're gonna do a graphic layout of our baby bullet curve, okay, and that's this tangent to tangent curve here. We got a curve and then we go into a larger curve like that, okay, and so there's a radius here and then there's a radius here that are tangent to one another, okay. So, and then from that what we want to do is we want to figure out the coordinates so that we could actually use a ball end mill and profile that, okay. So that's what we'll do here. So pencil, my trusty blue dot Vemco compass here, and we have another little Vemco compass here. This is kind of a special one for drawing small circles. If you have a lot of little circles to draw, this is kind of nice for that. And then we have a ruler, okay. So let's pick some numbers. Let's make them nice and easy. Let's do this one 1 inch and this one 3 inches, okay. And so 75 millimeters and 25 millimeters, okay. So let's do the big arc first, and I'm just gonna set my compass here. Yeah, I'm kind of cheating a little bit because I'm using the graph paper, and if I pick like increments of the graph paper for my demo, it's just all right. That looks pretty good. All right, so let's strike our first arc here. All right, hopefully that's dark enough you guys can see it, okay. All right, so there's our 3 inch, and then I'm just going to circle the center point there so you can kind of see it. Now I happen to remember that on the baby bullet that arc center was above that flat, so I'm just going to drop down a little bit here and below that center and say this is now my line that I want to be tangent to, okay. So now what we have to do is we have to draw an arc between here and here, okay, that's tangent to this arc and tangent to that line. So how do we do that? Now the cheapskate method is to set your dividers at 1 inch and poke around and kind of find the optimal spot, but that's just what that is cheating. So instead what we're going to do, we'll do it the proper way here, and I'm going to turn the paper because otherwise I won't be able to do it. Okay, so there's a line that's 1 inch off. All right, so what we're going to do is we're going to put a construction line there, nice light construction line, okay. All right, so that's 1 inch off. So we know that the center for this radius here lies somewhere along that arc, okay. Well, the other thing we can do is we can find the other foci of that arc by increasing, let's see, we're going to go to 4, okay. We're going to strike another arc here. Hopefully these open far enough. Okay, yeah, we're gonna make it. I forgot how big these open. All right, that looks pretty good. So now if I strike another arc here that's larger than this one by the amount of that radius, all right, that's my center point. So let's reset. So you can see having more tools, right? You could have several of these set for different things and move a little faster. So that's one reason for having lots of tools. All right, so let me stab that position. Okay, so now this should be nice and tangent to both, and it looks good. Okay. All right, so tangent, tangent. All right. So, one thing you can do to make this whole thing more accurate is to make it a larger scale. So you can multiply by 5 or you can multiply by 10 and get accurate, very accurate layouts. And when those scale down to your actual size, the coordinates are actually really good. So it's an old drafting trick there. Okay, so let me. So what do we want to do now? Okay, what we want to do now is we want to mark our starting point, which is straight up and down here. So this is our x0 coordinate line here, like so. X0, all right. And let's draw some little circles now that represent our ball end mill that's going to follow this. It's going to follow this curve. Okay. Oh, let's do this too. We're going to put a line between the centers here. Okay. All right, and that little intersection right there, that is the point of tangency between those two arcs. Okay. All right, so let's set this little guy. We're going to be using a 1/2-inch ball end mill. All right, excuse my arm. All right. All right, so now what we do is we basically just kind of start. Oops. Actually, I'm sorry, I messed up. So I need to draw 2 more arcs here, that are larger than these, that represent the center of the. All right, so we just need to increase that by 1/4. That's right. All right. So this one here. There we go. So that's the center line path there, and then we can do the same over here. I got ahead of myself there. I'm just gonna match up with that, but you guys get the idea here. Okay. All right. Hope this is making some sense here. All right. So I think this was already set. Yeah, it's looking good. All right. So now I'm going to start here. Hopefully, the lead in this one is harder. Okay, so that's my first coordinate. That's 0, 0 right there. So that's x0 and z0. Now for my next circle, in this case, I'm just gonna grab that spot where it crosses that line, just because it's easy. And you can, once again, you can do as many as you like. Boy, I'm out of practice with these tools, I'll tell you. All right. All right. And rinse and repeat. Let's keep going here. Let's get a few more. No, that one's not a good. Okay, you guys are starting to get the idea there. Okay, now I'm going to zoom in a little closer on this. All right, and then we can talk about picking those points off. Okay, so there I drew in some more circles. So this represents our ball end mill that's coming along here, and stepping down this curve and then following along, right? So. But what we can do now is let me add another line in here, okay, this little construction line. I mean, there's a line on the paper, but I'm just kind of extending it out a little darker so you guys can see it, okay? So now what we can do is, that represents x0, and this represents z0, okay? So, looking at the little the little pricks that the compass left, we can measure to those points quite easily. Okay, and here's an example: is our first move in x is going to be about 237, right? And then if I measure this way, okay, and I can get in there with a magnifier and look at that. Okay, I don't know, 8 or 10,000, something like that. Okay, and then I can measure to the next one, and I can measure to the next one, and I can measure to the next one. And so what I can do is I can create a chart over here of x and Z coordinates, okay, that I can follow to produce that curve. Now, in particular, if I scale this up, say 10x, right, you know, which is pretty big, all right, that's pretty big in this situation. You know, any little errors in my little drawing kind of get taken out in the wash when we shrink it back down to actually do the cutting, okay? So by measuring off of this X0 line and the Z0 line, you can establish those coordinates and do actually a really nice job, okay? So no computers, no fancy schmancy stuff, no internet, you don't even need Excel. Now the math guys out there, you know, you can create a chart in Excel pretty quickly because you know where the center is, and you can say that these are 5-degree steps, so you can calculate a bunch of triangles, you know, automatically in Excel and then generate an X and Z chart pretty easily, okay? So, but this is how you do it graphically. And you know, you can do shapes like that, you can do undulations, you can do all kinds of stuff with a little bit of patience. And you know what? You don't need a CNC, okay? CNCs are wonderful, but they make people lazy too. So now you're a computer jockey as opposed to a machinist jockey, okay? So how would you do it if you had to do it the hard way? If you know the hard way, the easy way is just that. It's easy, okay? So, but this isn't too hard, okay? You didn't know numbers, or not lots of numbers anyway, fairly simple stuff. And basically, I just slightly automated that process by doing it in AutoCAD with a couple of polar arrays and just pulling the coordinates. You know, I was just letting the computer do the math, basically, okay? So hopefully you guys picked up on that, and I didn't do too bad of a job explaining that, so thanks for watching that. Okay, so the other question that came up, and I made a little comment about it, was climb cutting versus conventional milling, okay? Climb milling versus conventional milling. So for those of you that don't know, the difference is, so you know, we can come across this piece in two directions. One is we can come from this side to this side, okay, and the cutter rotate. Let me put it in neutral. The cutter rotations like this. Actually, let's just do that. Make sure I don't hit. So that's climb cutting, okay. Now, what happens with climb cutting is that when the tool enters the work, it's at full chip thickness instead of the chip going. I have a Sharpie on me here. So the chip, you know, the stylized chip looks like that, right? Okay. So it enters the cut at the full thickness of the cut instead of ramping in from thin to thick. Okay. So it's choop, choop, choop. It's biting into it. So it uses less energy actually to cut, and in general you get a smoother finish. Okay. But on manual machines, it can run away from you. The thing can act like a rack and pinion and actually pull you into the cut, which is why there's a lot of information out on the web that says never climb cut on a manual machine. Well, I don't like absolutes, okay? It's just not true, okay? You can climb cut on a manual machine, you just have to be careful and aware of what can happen, all right? So there's climb cutting going that way, all right, with the cutter this way. And then this is what they call conventional, which is this way. So this is from thin to thick, okay? Now both work fine, but in general, the climb cutting produces better finishes, okay? So you shouldn't be afraid of it, you should be careful with it, okay? Just be aware of what you're doing. So if you have a, you know, a big cutter like this that's a 2-flute and you're running in stainless steel and you're trying to take a big cut, no, I would not climb cut that with that, I would conventional. You have a multi-flute cutter and you're taking a light cut in thinner material with a good setup, it's no problem. You guys see me do it all the time, okay? So you shouldn't be afraid of it, you should experiment with it and understand it, okay? So we'll just do a little demo here. You know, this is a 3-flute carbide end mill. Let's touch off. All right, so we'll take a little cut. All right, and you can see it's just behaving itself. The weight on the handle is actually quite light right now, okay, because it's kind of self-feeding at some level. All right, and then here's conventional. Much more pressure on the handle. Okay. Okay. So as you can see here, climb cut. The world has not ceased to rotate. It's still, you know, I'm still alive here. Nothing bad's happening. Okay, and then conventional. So I encourage you guys to play around with that, okay, and understand the limitations of it. You know, everybody's got a bad climb milling story, kind of like everybody's got a bad drill press story. So just be aware of what you're doing, use it, understand it, and know when you can apply it. Because if all I'm going to do is climb cut, then I got to go back across and take. So I'm doing twice the work. Okay, I'm doing twice the work that I need to do, all right? And this is why old guys bury young guys, is because they understand some of these things, and they don't look like they're working hard at all, but they're being efficient. So anyway, that's climb versus conventional.